Pavan, and we are presenting TSP on graphs using reinforcement learning. So these are our teammates. Uh, Coming to the introduction part, the first thing which comes into our mind is what is traveling salesman problem. So here, what happens is, we have to find the best way to visit all the graph nodes and come back to the starting in the shortest trajectory or shortest route. So this is the main objective of the traveling salesman problem. And traveling salesman problem is a NP hard problem, means it can't be solved in polynomial time. The applications of traveling salesman problems are enormous, which include in the transportation logistic industry. Basically, to find the best possible route, we have to use the traveling salesman problem. Now, background study. So the next question comes into our mind is why to use reinforcement learning. So the main purpose of reinforcement learning is we don't need any data. Our algorithm, our system will do exploration and exploitation and find all the possibilities. So we don't need trained data. So that's the main thing. And the rewards and the state and the system, everything will be predefined, including the policy, which we'll discuss in the following slides. So, coming to the related works, so these are the two papers which we have researched, which we have read. First one is playing a tree with deep reinforcement learning. So here, what's happening is the first layer is a neural network, and the next one is a Q learning. So we'll be playing a three game using reinforcement learning. So that has given great success. The next paper is learning combinational optimization algorithm over graph. So here we have to optimize the NP hard problem. So by drawing different graphs, the optimization could be expressed in very fast way. Now,
Myself, Ponish, roll number is 20150, and now I'll be saying the methodology. We have implemented this whole part using reinforcement approach for the traveling function problem, and it is based on Q learning and structure to VEC graph embeds. So first we'll be importing the necessary libraries we want, like NumPy, PyTorch, and Matplotlib for visualizations and scikit-learn for training the algorithms and all those things. And then we will be creating the graph instances. Before we create the graph instances, we'll be using the NumPy library for creating the random numbers. From that random numbers, we'll get in coordinate. From that coordinates, we'll plot the graph using Matplotlib. In this way, first we'll do, and then we'll be defining the state cell. States which will be taking the actions and all those things, and state environment all will be done. And if after defining the state, in state function, we'll be doing the Q function also. And in this Q function, we'll be designing a neural network that has some parameters, and that has a parameter function of Q of S comma A. S is nothing but state, A is nothing but actions. And then after defining the Q function class, it will act as a wrapper around the CN, like the neural network. It can be named, it is named, it is also known as QNet. And after that thing, we'll be defining the experiences and memory. And then now we'll be writing the functions which can be help us to find the solution length and deciding which is the final state or not. And after getting the random information, the nodes of the graph, like by this, the main crux of this function, writing these functions is like we can know what is the starting point, what is the ending point, and what is the total length of the path which we have designed. That whole will be based upon this code. And after that, training, and after that we'll be writing the training code for the hyperparameters. Then after we'll be giving the main method in which the root duration will be going on, and then we'll be training the loop on that, because if you train the roots which we get iteratively, then we can get a best output. So then after getting this outputs, then we'll be seeing the training matrices, like how accurate it is. And then after getting like first we'll run for some epoxer, then after that last we'll run for some more than 100 epochs. At that time we can get a best output and best result. After that, after getting the best results, we'll be taking some top 50 parts, and for the 50 parts we'll be doing the parts set using MATLAB. This is the methodology, sir. And now the results which you'll be getting in our code. So first we'll be here representing two graphs, sir. First graph is about the training iteration and loss graph. For in the first step, you can see when the amount of training iteration is less, like it's near to zero. That time the loss function is more. Loss is nothing but the original output original output minus the like original output which you want minus the output which you got. So the graph, if you see, there is a lot of variation. If you increase the number of iterations, training iterations, then it is getting less. And then the number of iterations, the average length graphs are like the episodes nothing but number of times of running this thing code. At that time, if you increase the episodes, then the average length of the total graph or map, like not map, like path is getting reduced. We can see in the graph. It is the pictorial representation in the graph, sir. And at last, I said you will be getting the paths generated, sir. There are some examples of the paths which you have got after generating those things. And coming to the FHS scope which we can more deploy in this project, we can improve the way the sequence are handled, sir. We are getting the best routes, but we can try to get best routes with less number of epochs. We can improve the model efficiency, and we can get a better graph structure also, and we can get more tuning parameters, hyper parameters, so the results can be obtained very fastly. And then we can optimize the code around the GPU, and we can use some more better models to get better accuracy results. And then coming to conclusions, sir. As we know, reinforcement learning is getting developed in many domains right now, and in case of environments can be easily simulated. And in this paper, we have explored the approach that can be used in PSP by combinational optimization problems. This project can be deployed in real time also. We can take different number of cities in India or anywhere, and we can just try to get shortest paths using the RL by using this neural network. And then this, this is the way which we will deploy it, sir. This is the reference which I have used to do our project, which helped a lot in the coding part and all those things. Thank you, sir. Thank you, sir.
So coming to the code part, as our project is of traveling salesman problem based on RL, where we need to import some libraries. Which are these libraries? We are also using TensorFlow and Torch. So we need to import the the required libraries. Since our project is of traveling solution problem, it is based on graphs. First we need to create a graph. So here for creating graph we are using this method, and in this method returns the following matrices which are of n comma 2 in dimensionality and n comma n, where n is the number of nodes. And the below method is there. In this method we are going to represent the graph in a graphical way. So this is a sample example of the graph which we are defining. And as you know, the RL is defined by state action functions. So first we need to define the state. So we now define the state as in the tuple format, where W is the weights and node coordinates are denoted by chords, and partial solution is like list of nodes that are being visited. And we also define a function called state to trans, which translates such tuples into tensors, because as we are assuming our state as a tensor, we are using state to tens method so that we can represent the state in tensor format. So this part of the code will do the state to tens thing. and for the queue function. So the neural network will be parameterized into q of s comma a, where s comma a are state and agent. So the input state and the output is a vector of n size containing q of s comma a for each of n of a actions. Since there are n nodes, for every node we will have for every node we will have actions. So this is a whole class of qnet where we are having some sub methods, and we are defining the state action functions here, the queue function. So this is the init method where whenever we will initialize the class of qnet, these three pointers will automatically be initialized, which are embedded dimension and t. So as we are discussing about queue functions, we are using 5 dimensions for nodes to represent the node of node of any state. So those are the dimensions, extra layers, and all these things are there. So these are the parameters which we are using in here, and this method forward is there. So this method is to go to the next nodes and deciding the actions and the value, what is the reward we are getting. All the things are described in the forward method, in this method. So and going to the next part, we are using QNet, and these are the inputs that are given here and in the above, where 3 and t comma 2 are these values, the dimensions and extra layers and the coordinates, and also we told that we are using 5 parameters, such that we are giving all the parameters here, and we are representing the state in a tensor. So just we are printing the output of the state, which is in the form of a tensor. It looks like this. Now we need to define the queue function, so which will act as a wrapper around the neural net QNet. Since we defined the neural net as of QNet in the QNet as a class, and we can manipulate it to do TSP solutions. So we need a queue function. So we are initializing a queue function here. So this is the class of queue function. Here this is an init method where in our model, this is the model, and we need an optimizer and a scheduler. So whenever we are calling queue function, all these must be initialized unconditionally, no need of separate initialization. Then we are predicting the batch of one only called at the inference time. And here we are checking the best action. So what is the best action, so that we will get the maximum reward. So here w is of the state, w is state, and this is the rewards, and we are sorting the rewards using index, and we are running a loop of all the rewards, and we are taking the best. So and this is update. So we are taking a gradient step using the loss computed on a batch, and state TSRS is a list of single state tensors, since we are using our state as tensors, and WS is the list of W tensors. As I discussed, W is the weights, and actions targets everything. So here we are estimating the rewards based on the above method, and it is returning the loss value. Um, Here we are getting the experience. Since rewards and actions, we are calculating rewards and actions, we are getting some experience. So we will now now a tuple representing an experience in the memory that contains such experiences. An experience is composed of state and action tuple and the corresponding next state and reward. So it works like a Markov rule. The next state can be n step after the state in the case of n step q learning. So here if it is an n step q learning, it is not mandatory that we should go to only the next step, but if it is two steps mandatory, two step q learning, then we will go to the next two states, and there also we will consider the result. And in the experiences, we save states both in the tuple and tensor representations in order to avoid computing these somewhat expensive translations after the experience has been stored. So here we are calculating the experience. Since similarly this is an init method where whenever we call this memory, all these pointers will get initialized, and this is the remember, since we are getting self and experience, if the memory is less than capacity, then no need of appending anything to the memory. And after these computations, we are calculating the experience and adding to it. Next, these are somewhat useful because of for some optimizing of the code. Here the total distance, it represents the distance between two nodes based on the weights, and the final state is final or not. Since in the TSP the initial state is the final state, we need to know that whether we have reached the initial state. So to keep track, the current state is initial or not. So if we reach the initial state, then it is the final state, and the whole nodes are being traversed, and get the next neighbor in random. So here in RL, in general TSP, we are going to uh, go to the next node, and after that we are going to next node. Like that, we need to create a path to reach the final state, right? But here we are choosing the neighbor in random, and we are learning whether which neighbor is good to reach. Next, these are some hyperparameters used in the code, and here we are initializing the model. So creating a new model. So these are some error handlings, like if the name is already initialized, if the model is already initialized, then we are this is like a small error handling part. Uh, and coming to the next, we are training the model. So here is the part where we are gonna train the whole model. So here we are using the PyTorch variable. Here we are using the PyTorch variable, and here these are the things which we are using as QNet, the model, as we have defined init underscore model. So we are having some pointers that are being initialized unconditionally. So we are initializing that to these variables, and we are creating the memory capacity as since we have used it for this as an experience. And these are matrices we are using. We are just initializing the matrices and matrices and lists for keep tracking of the nodes. Next, we are running a loop of all the episodes, and finally here this while not in file state final is until we are reaching the final state, we need to run the loop, and we need to execute it. And so here we are using if the length of solution is as I discussed of n step QL, we need to go to n forward steps, and we need to analyze the rewards of actions for that state. And if we, here so this block will get executed if it is n step q learning for the sake of experience. And if it is the final state, then there is no need of going to n steps forward, since it is the last state. So one step q learning is fine. So at that place, this part of code is get executed. And after doing that, we are going to next state, updating the like going to the next state. This is done recursively. And since this memory is like we are calculating the length, the path. So all those things are calculated in below this if block. And for getting the value, we are multiplying the gamma into best reward, where we will get the exact value of the experience gain. Now we are saving the model here, below part we are saving the model. And according to our analysis and our running, the code have 3000 episodes, more than 3000 episodes, which you can see here. The code have approximately the code have approximately 4000 episodes. So after modeling the after training the model, now we need to inspect the training matrices. So as in the before itself, we have done we have initialized some empty variables. So here we are using them. So this is the training iteration. So here the loss function starts at the top, and it decreases continuously, some places it is increasing. So this is based on the some episodes. This is based on iteration and loss, and this is based on average length and episodes. Since we are seeing an optimal graph, we can see our model is somewhat better. So here in this part, we are rerunning the model and looking into the paths. So as our project is of containing the possible optimal traveling salesman paths in the given, so the given output we outputs. So these are all of files. Since maybe the file will be zip file or anything, we are doing that analysis also, and then we are doing the checkpoints, and again we are doing the path solution where we are plotting the paths, and again we are keeping the paths in the model that we have trained, and after that we are after testing, we are printing the figures. So this is the output. So here in this graph, assume this is the start point, and we are going in this path, and finally we are reaching the end point. And this is that predicted by model. This is the model length, and here this is the random length. Like we are choosing a random variable and going through that random variable by completing the path. Then we are getting average length as this one. Model is somewhat optimized, definitely we will get our model as good value. And you can see for other samples also, if this is the if these are the coordinates, if we go by this length, then we will see model length of model will be of 2.89. But if we go randomly, then we will get this much of error. This is an error. This is a random, choosing the neighbors as random but not without algorithm. Similarly, these are some examples. So this is how the code works. Finally, we are getting the outputs. We are also comparing which is good, whether random or the model. Definitely, as our model is optimal, we our code is working properly. So thank you for giving us this opportunity.